Hey guys, today we're going over hemostasis. What that is basically the stopping of blood flow. If you were to get cut, you need to stop that blood flow. So your body's going to regulate that so you don't bleed out. So the first thing that happens when, let's say you have a cut, right? That's what's going to happen is a vascular spasm. It's a pain reflex, and what that pain reflex does is going to stimulate smooth muscle so that it constricts or it contracts. And what this is going to do is it's going to vasoconstrict. It's going to decrease blood vessel diameter. So instead of having normal blood flow through that area, it's going to decrease that so you don't pump more blood out. The second thing that's going to happen with hemostasis is a platelet plug. So over here we have a regular platelet. It's not activated yet. It's flowing in the bloodstream. And then it encounters rupture in the epithelial layer, and it will be exposed to collagen down here in this layer. Once it's exposed to collagen, these epithelial cells will produce something called von Willebrand factor, and that von Willebrand factor will bind to the platelet. And on this platelet we have von Willebrand factor receptors. Once we've bound to those receptors, a couple things are going to happen. We're going to release a couple things inside of the cell that will affect more platelets aggregating around this clot and creating this platelet plug. So let's move over here. Here I've drawn it where it's attached, but let's move over to here because I've kind of drawn it out better. So here we have our platelet that's activated. Once we've activated it, we have inside of these alpha granules as well as dense granules. Alpha is bigger, dense is smaller. Let's start with alpha. Alpha is going to secrete thromboxane. Thromboxane is a strong platelet activator. If you stimulate thromboxane, then you're going to cause a bunch of other platelets to become activated, and they're going to want to bind. You're also going to stimulate von Willebrand factor. That's just so that we can bind more platelets to this site of injury. And then fibrinogen. Fibrinogen is what connects platelet to platelet. So while von Willebrand factor connects platelet to collagen, fibrin is what's going to connect your platelets together. So fibrinogen, once it hits a receptor, it's going to become fibrin and it's going to connect all your platelets together. Moving on to our dense granules, we're going to secrete adenosine phosphate. ADP is also a strong platelet activator. We're just activating platelets left and right here because we want to form this clot as fast as possible. We'll also secrete calcium. Calcium is going to do a couple things. Within the platelets, you'll have actin and myosin, and you can pull those platelets together closer and cause the blood clot to become more dense. Calcium will do that, as well as activate snare proteins to release these alpha granule contents and the dense granule contents as well. And that's all stimulated by this von Willebrand factor to start out with. Okay, moving on for our third step for hemostasis, we have a coagulation cascade. We'll have an extrinsic pathway as well as an intrinsic pathway. Let's say internally you get some type of rupture of a blood vessel. It's internal, it's not external. So you're going to have an internal cascade. And so there's a bunch of factors that go into this, and they're pretty generically named, but they're important in this cascade because it all leads to a common pathway where your extrinsic and your intrinsic kind of meet up and form that fibrin clot at the end. So your fibrin clot and your platelet plug are going to work together to close this hole. So first off, you start with 12. It activates with contact with collagen, just like your platelets activate with collagen. And then it's going to this is now going to activate 9, 9 is going to activate, or 11 is going to activate, 11 is going to activate 9, 9 will become activated, 9 will then form a complex between factor 8 with phospholipids and calcium, and what this is going to do is continue that clotting factor. Finally, once we form this complex, we're going to activate factor 10. 10 is now in the common pathway. If you look over here, our extrinsic pathway will also activate factor 10. Let's scroll over to extrinsic pathway first. With tissue damage, epithelial cells will release a factor 8 that will become activated, as well as tissue thromboplastin. These two will work together to activate factor 10. With factor 10 activated, we will now form another prothrombin activating complex, and that will be with factor 10, phospholipids, and calcium, much like this previous one with 8 phospholipids and calcium. Once prothrombin is activated, it will turn into thrombin. Thrombin will activate factor number 13. Thrombin also activates fibrinogen, turning it into fibrin. Fibrin and factor 13 activated will now form a fibrin clot. And those are your steps for hemostasis. Really quick, I want to scroll over here to clot degradation. So you formed a clot, and now you want to undo it. So with clot degradation, we have fibrinolysis. Plasmin is going to degrade the fibrin that we just made from the clot cascade. First off, you start out with plasminogen, and a tissue plasminogen activator is going to hit that plasminogen, activate it, and it's going to turn into plasmin. Urokinase also plays a role in activating plasminogen. And then finally, that plasmin will hit fibrin. Fibrin now degrades. You've degraded that clot so that it doesn't keep forming. It's really a regulation of clots. And that's so you don't have embolisms and just a continuation of a clot throughout your whole blood system. And that's hemostasis for you.